Hello students, welcome to the Team Curiosity e-learning classes. In this lecture we are going to derive the equations for displacement and velocity of a particle which is executing simple harmonic motion at any instant of time. Let us consider a particle which is executing simple harmonic motion along x-axis due to the restoring force denoted by capital F. We have learned before, that is, force is equal to minus kx. Make this as equation 1. Here, negative sign denotes that force is restoring in nature, where k is equal to force constant, x is equal to displacement. Again, we know that force is equal to mass into acceleration. Make this as equation 2, where m is equal to mass of the particle, a is equal to acceleration. By equating equation 1 and 2, we get a new equation, that is, mass into acceleration is equal to minus k into x. By taking m to the right side, we get acceleration is equal to minus k by m into x. Also, I can write acceleration is equal to minus omega square into x, where k by m is equal to omega square. Here, omega is the angular frequency of the SHM. As we know, acceleration is equal to dv by dt, so I can write dv by dt is equal to minus omega square. Also, an interesting thing is that I can write dv by dx into dx by dt instead of writing dv by dt. So, my new equation will be dv by dx into dx by dt is equal to minus omega square into x. As we know, dx by dt is equal to v. We can write v into dv by dx is equal to minus omega square x. Now we'll do the integration both the sides by taking dx into the right side. Let at time t is equal to 0, displacement x is equal to x naught and velocity v is equal to v naught. After some time t is equal to t, x is equal to x and velocity v is equal to v. Now putting proper limits, the equation will be integration v naught to v dv is equal to minus integration x naught to x omega square x into dx. Using the rules of integration, we get v square by 2 limit v naught to v is equal to omega square into x square by 2 limit x naught to x. Performing the subtraction from upper limit to lower limit, we can write v square minus v naught square is equal to minus omega square whole into x square minus x naught square. By taking v naught square into right side, the new equation will be v square is equal to v naught square plus omega square x naught square minus omega square x square. By taking root over both the sides, we get v is equal to whole root over of v naught square plus omega square x naught square minus omega square x square. By taking out omega square from the root over, we can write v is equal to omega whole root over of v naught square by omega square plus x naught square whole minus x square, where v naught square by omega square plus x naught square is equal to a square. Here a is the amplitude of the oscillations. Now we can write the equation as velocity v is equal to omega whole into root over of a square minus x square, which is a very important relation, that is, velocity is in terms of displacement. Can I write velocity in terms of dx by dt? Answer is yes. So I can write the above equation as dx by dt is equal to omega root over a square minus x square. Make this as equation 3. From equation 3, taking dt into right side and putting integration, we get integration dx by whole root over of a square minus x square is equal to integration omega dt. As mentioned before, at time t is equal to 0, displacement will be x is equal to x naught. After some time t is equal to t, displacement x is equal to x. Now putting proper limits to the integration, we get sin inverse x by a limit x naught to x is equal to omega t limit 0 to t. Also, we can write sin inverse x by a minus sin inverse x naught by a is equal to omega t. By taking sin inverse x naught by a into right side, we get sin inverse x by a is equal to omega t plus sin inverse x naught by a, where sin inverse x naught by a is equal to phi, where phi is the phase difference. So we can write the equations sin inverse x by a is equal to omega t plus phi, which becomes x by a is equal to sin of omega t plus phi. By taking a into right side, we get x is equal to a into sine of omega t plus phi. Make this as equation 4. Equation 4 is the displacement of particle as a function of time. As we know, velocity v is equal to dx by dt. So by taking derivative both the sides, we can write dx by dt is equal to derivative of a sine of omega t plus phi, which is v is equal to a omega cos of omega t plus phi. Make this as equation 5. Equation 5 is the velocity as a function of time. Hence, the required equations for displacement and velocity of a particle which is executing SHM are as follows. Displacement x is equal to a sine of omega t plus phi and velocity v is equal to a omega cos of omega t plus phi.